Hey guys. So today, Goodbye 2020 happened, and I did my first contest in a long time. And from what I know, if I don't fail system tests, I will be keeping International Grandmaster because I have this minus 14 right now, and that's enough. That'll put me at 2608. Okay, so that's cool. And yeah, in other news, I'm going to be. This might be the last video ever with my terrible mic since I did get the new one now. And again, my family is awesome. And so I'll be testing that out soon, and hopefully new videos will have better sound quality. But this should hopefully be the last video that's so terrible. Okay, so two things will happen now. One, we'll hope system tests happen, and two, I will go over solutions for the ones I solved. I have an idea for G. I'm not entirely sure if it's right because, yeah, but who knows. Okay, so let's start with A. Let's see, it's picking up sound, right? Okay, so let's start with A. And in A, you have a number line, and you have a point here, and a bunch of other points here are on this number line. Like these are points in 2D space. So for example, the sample will have points at 1, 2, 4, and 5. And what it asks you is, of all the ways to make triangles out of 3 points that aren't degenerate, like for example, so it has to use the red point and then 2 of the green points, it asks you how many distinct areas can you have of the triangles. So n is 50, the coordinates are at most 50, there are at most 100 test cases, so all the constraints are small. So in fact, there are only at most n choose 2 triangles, since you can pick any 2 points, which is n times n minus 1 over 2, which is at most 50 times 49 over 2, 1225. So there aren't that many triangles, which means that you can straight up create these triangles and find their area and just check all of them. And then you put them in a big list and then just count the number of unique ones. And so the way to find triangles is simply the area formula, base times height over 2. But since you're only checking for unique values, you can sort of just remove this over 2. And because you know that this point is at coordinate 1, 0, or no, sorry, 0, 1, we know that h is a constant 1. So we can actually remove that too. Actually, I'll cross out the over 2. So now we're really only interested in the unique values for the base. And the unique values for the base is simply the distance between every pair of points. So we can compare 1 and 2, their distance is 1. We can compare 1 and 4, their distance is 3. We can compare 1 and 5, their distance is 4, and etc. And we do this for all pairs of points, and then you can stick them in a set or something. Like in my code, I just used a C++ set, and that does it. So just count the number of distinct ones. By the way, I'm not using the writing tablet this time. I still want to. I'll use the writing tablet for like screencasts as practice because I want the solutions to be better. And if I'm struggling with the writing tablet the whole time, it's going to take like 12 years to explain A or something. So that is not what I want. Let's see. A is accepted. All right. So B asks, what does it ask? You have a list of numbers. So for example, 1, 2, 2, 2, 5, and 6. And it asks if you can increase each number by 1. You can either like for each number, you can either increase it by 1 or leave it unchanged or increase it by 0. And what you want to know is, given that you can do these operations on each number at most once, how many distinct numbers can you have in like the best case? Okay, now the first thing is, if a number is distinct, then let's like go through the numbers in ascending order. Since we can only make numbers bigger, so like moving a number up here might make it impossible to, or might make it so it matches with a number up here, but a number like 2 will never affect a number like 1. So we iterate in these so we can iterate in this order to find out what affects what. So if we have one distinct number, then like it's always going to be distinct and there's no reason to increase it. If we don't increase it, then the number of distinct numbers will be unchanged. And if we do increase it, then it might coincide with some other number and then stop being distinct. So we either gain nothing or lose one if we do increase it. So there's no reason to increase a number that's by itself. But if we have numbers with multiple occurrences, then like these occurrences are kind of wasted. That is like yeah, these occurrences are wasted. Like what's the point of having multiple 2's when we can just not have multiple 2's, right? Because given that we have multiple 2's, if we say increase one of these, we're still going to have this 2. So if we increase something that has multiple occurrences, as long as we don't increase all of the occurrences, then we won't lose anything. But since we get a new number, we might actually gain something. Because, for example, in this array, 3 doesn't occur anywhere. So another part of the strategy is if a number has multiple occurrences, you can increase one of those occurrences by 1, and then you can possibly get a new number. And then leave the other ones unchanged. So for example, leave these 2 unchanged. And then here we have this 3, but we can't touch this 3, so that's pointless. Then we have this 5, so it's distinct, and we have this 6, so it's distinct. So the strategy is, if it's distinct, don't touch it, otherwise there are multiple occurrences to that number, so you can increase one of the occurrences, and that will give you the best answer. In terms of implementation, I just also use the set because I'm lazy, so you can do something like that. Like for example, stick this 1 into a set, stick this 2 into a set, and then add 1 to this, and then stick the 3 into a set, and then we already have the 2, so that doesn't affect anything, or we can have the 5 and the 6, and then print the size of the set. I'm sure other languages have this sort of similar thing. Things are in queue. Okay, everything's 2 seconds, right? Alright, just to be safe. Did they make all the problems 2 seconds, even A? Okay, so I guess that was unchill. Alright, so C asks about strings. And basically you want, you have a string. So for example, B, A, B, B, A. And what you can do is, what you want to do is you want to make it so the string has no palindromes in it, or specifically palindromes of length greater than 1, because every substring of length 1 is a palindrome. So you want to make it so it has no palindromic substrings, that is like contiguous groups of characters. It is contiguous, right? Because otherwise, like, it'd be stupid. Yeah. So we're asking, we want a string that doesn't have any palindromes of length greater than 1. And what we can do in one operation is we can pick a character and change it to something else. So for example, I can change this to X. And we want to find the minimum number of changes we need to do to be able to convert to a string like this. So the question is, what even constitutes a palindrome? Like, for example, in BA, we have 4 palindromes. Or no, I mean, there's no reason to give a number. I mean, we have these palindromes. This one, and this one. I think that's it. Yeah. So like, look at this nested structure, right? So this palindrome of length 2 is entirely contained in this palindrome of length 4. And this palindrome of length 4 is only a palindrome because this palindrome of length 2 is. So we don't necessarily have to get rid of this palindrome of length 4. What we really only need to do is to get rid of this palindrome of length 2. Because say I do get rid of it, then any palindrome that has that palindrome nested will also no longer be a palindrome because like its inner parts isn't a palindrome, so the whole thing can't be a palindrome. And so this works for even lengths and also works for odd lengths. For example, if we have A, B, A, B, A, if I get rid of the palindrome of length 3 in the middle, as in I change this to X or something, then the whole big thing will also stop being a palindrome. So what I'm saying by this is that we only care about palindromes of length 2 and 3. Because if we have no palindromes of length 2 and 3, like a palindrome of length X is a character plus a palindrome of length X minus 2 plus another character. So if we have none of these, then like kind of inductively we can't have any longer ones. So we only care about palindromes of length 2 and 3. With that in mind, how do we change the answer? How do we find a solution for that? And the answer is we can simply greedy it. And the reason is because when we do something like BA, we have this palindrome here. We have to get rid of this somehow. So the only thing we can do is change one of these two characters to get rid of the palindrome. So if we change the character on the left, then that's fine. But if we change the character on the right, then notice we have this other palindrome BB, which is like further to the right than this one. So changing this character will take care of both palindromes. And in general, if we assume we've already fixed this, if we assume we've already fixed every part of the string before this, then like, because we only care about lengths 2 and 3, there's no possible palindrome that could be formed with this left character. But there are possible palindromes that can be formed with the right character. And therefore, it's like always better to use the right character, assuming we iterate in like this order. Assuming we go through the string and kill palindromes in this order. So now, since we're always going to change a character on the right, we can, for each character, look for some palindrome to the left of it. And so we can say, does this character form a palindrome to the left of it? And that means either it's equal to the character 1 before it, or it's equal to the character 2 before it. And if neither of those are true, then this is not involved in a palindrome, and therefore we never have to change it, because it's like not a big deal. But this character is. This character is involved in a palindrome of 2 before it, or like of length 3, because it's equal to this character. And notice that this character doesn't matter, because no matter what, it's going to be equal to itself when flipped. So because this is involved in a palindrome, we want to change it to something. So let's change it to something like X. And then now we have no more palindromes, because this used to be involved in this one, but it no longer is. So the strategy is just to go from left to right, and basically ask for each character, is it involved in a palindrome to the left of it, either one character or 2 characters down, and if so, change it. Now the question is, what do we change it to? We want to make it so we don't create any more palindromes to the right. Well, notice that this character, because we only care about palindromes of length 2 and 3, is only going to be compared with 4 characters. The A, the B, or the character like the one 2 before it, the one 1 before it, the one 1 after it, and the one 2 after it. This is only 4 characters, but we have 26 characters in the alphabet. Which means that like we have 22 other characters that won't ever form a palindrome. And so what that means is that no matter what we do, like no matter what these characters are, we're always going to have something that we can change this to get rid of the palindromes. So it ends up not mattering. We can sort of treat it like replacing it with some like extra character, like replacing with a number or something. Like we replace the first character we move with a 1, we replace the second one with a 2, and so on. And then we just keep going like that. So then with that, we can do a sort of greedy approach and just sweep from left to right and replace any character that is involved in a palindrome to the left of it. This is optimal because it's always better to use the right one, or it's always optimal to use the right one. And if we have a palindrome like this, we have to remove some character. So we're removing the most optimal character, and we have to remove it. So it's like optimal. That's the argument for it. Okay. Let's check my submissions again. We passed C. Okay. for problem D, we are given a tree, like so. Can draw the sample actually. Let me see. Oh, that's terrible. Okay, let's do something better. Which means I'm going to be computing these values offhand. We are given a tree, and every node has a value associated with it. So for example, 1, 2, or 1, 6, let's do some sneaky magic here. 2 and 5. And basically, we're going to pick some value k. And then we're going to color the edges in one of k colors. And essentially, say we make this edge orange. I'm going to do circling here. So say cyan, whatever it is color 1, turquoise. No, it's like light blue something. And then purple is color 2. And orange is color 3. So let's say I assign a color to each of the edges. We have this, and then this, and then this. Now we're gonna look at the components of the tree that are like formed by nodes that are connected to it. Like for each color, we consider the components of the tree that are formed by all the nodes that are connected to at least one edge of that color. So for example, like for this, for the blue, we have this tree that uses these 3 nodes because they're connected to blue edges. For the orange, we have 4 nodes because we're connected to, 4 of them are connected to the edges, or orange edges, specifically these. I'm trying to keep the original, like the nodes are going to be in their original position in this drawing. And then the purple is going to be like this component. So each of these colors are separate. Like for example, just draw some dots around this. And now the values stay the same. So we still have the original values of each of the nodes. 3, 6, 1, and 2, and 2 and 5. And now for each color, the value of like this color is the component with the maximum sum of weights. So for example, this component has weight 3, but this has 9, so this one will be the one we take, and it's the maximum. This one has 11, and this one will be 7. And then the value of the whole coloring is the sum of the values for each of the colors. 11, 9, and 7, that would be 27. So that's that. And that's the statement. So for a given color, we're interested in finding the maximum value of a possible coloring. But that's not all. What we actually have to do is we have to solve it for all possible values of k. That is, we have to solve it for k equals 1, 2, ... n minus 1, because we have n minus 1 edges. So having more than n minus 1 colors is stupid. And we have to solve for all of them at once. And of course, n is like huge, 10 to the 5th. So there's no brute force that can happen. So that's the statement. Let's get into the solution now. And the solution hinges on like a couple of observations. So first of all, consider some coloring like this one actually. Let me redraw the tree, but with the colors actually like so. So for example, we have blue here, we have orange here, we have purple here. Sorry for drawing over the nodes, I don't like it either, but what can you do? 2 and 5. Right. Now look at this. We have 2 orange components. Which means that like in the orange subgraph, like this whole component's going to be wasted, right? But like why are we doing that? Why would we waste a component when we can instead make these nodes useful in some other subgraph? For example, we can make this edge blue, or we can make it purple. And then that way, whichever node, like the node that isn't attached currently to the blue component, which would be this one, or the node that isn't attached to the purple component, which would be this one, will be included. But it would be totally wasted in the orange component. there's no reason to have two disconnected components because one's going to be totally disregarded. So if we have at least two components, if we have more than one component, we can like sort of fill it in with some other color. Because like if this orange is disconnected from this orange, then there's some other color that disconnects it. So we can instead fill these orange edges with whatever color we have that disconnects it. Or some other color. Like some other color adjacent to the nodes. And then that would add to the values of the components of the other color because we get more nodes. So the first observation is that we only want exactly one component, or we only want at most one component. So at most one component per color, that is. Sorry for the handwriting. I promise this will get better soon, just like the microphone, just not right now. I'm not ready to use the writing tablet yet, it's too hard. And so with at most one component per color, that means like we're going to capture like entire components at once. So now let's do a sort of different thing. Let's try doing some contribution to the sum. How many times is a given node going to be included in some component? Or included in the answer, let's say. So this node, for example, is inside the blue component and it's inside the orange component. So it's going to be included twice, once for blue, once for orange. And in general, because we maintain that we have at most one component per color, every component is going to include all of the nodes that are like inside of it. Or like every color is going to gain all of the values from the nodes that are in its color. So for example, this wouldn't be orange. We would color it like purple or something. That'd be better. And just draw over it. Yeah, perfect. So we would color this purple. Now we have exactly one orange component, which means this node will be included in orange and it will be included in blue. So a given node will be included in all of the components that it's part of. Meaning that the value of a node is the number of distinct colors of the edges that it's adjacent to, or the edges that like go to it. Right. Now we're getting somewhere, because now we can count values. And there's like one final step that sort of directly follows from this, but at the same time is still sort of hard to get. That consider some node. It will be, wait, does this still have multitest? No, it still does. Nice. So consider some node. An upper bound on the number of times it can be included is its degree. Because like if there are 7 colors, but this only has 3 edges connected to it, then there's no way it can be included 7 times. It can only be included at most 3 times for each different color. And the second part is now we sort of want to like transition from we want to transition from like solve the solution from 1 to the solution for 2. And then we use the solution for 2 to figure out the solution for 3 and so on. Because like the solution for 2 is going to be basically the same as the solution for 1, except we just color in some component. Like we recolor some of the vertices to we recolor some of the vertices in this one to the new color we get. And then we do the same thing here. Now the question is like, what does recoloring get us? That's the main idea of this. And the answer is, let's find out. The answer is, let's find out. Yeah. By the way, I was doing very well, like before G started to exist. Like I was very fast on A, B, and C. It was sad. My rank went down so much, like after I just didn't get G. But whatever. So I'm drawing this tree one more time. I think this is the last time I'm going to need to draw this tree. But in case not, I'm going to make a copy of it. Because why not? Okay, so we have a copy of this tree. Now I can take another one if I need to. So this is the answer for k equals 1. Every node is included exactly once. Now the answer for k equals 2 is a bit different, because we know we're going to because we don't want to like split one component into two, we're going to start by taking some edge that's like from a leaf or something. And then we're going to like take a bunch more leaves until we get to like until we stop. And so the basic idea is and this is sort of intuition about trees, is that every component is going to like it's going to affect the value, like the number of distinct edges for a node for exactly one node. And that's the whole idea from these observations. Because if that wasn't the case, then like what would happen? Then there would be two nodes that have like new colors next to them. But that would mean that like that just sort of implies that we're cutting some component into two. Because like for example here, if we make it so this has that and this has that, then that's just not going to work. Because now we have two red components and that's going to be invalid now. So that's not a good thing. Okay, now we're system testing. And it's going to take years. Okay, well, let me try and figure out a way to prove this. Like the idea is that it only affects the value of at most one vertex. And specifically, it can increase it by one or, yeah. It can only increase the number of times a vertex is included by at most one. Okay, I guess we can prove it like this. So consider that it does it by more than one. That is, this increases by one and this increases by one or something. We'll think about it for a single edge and then extend it to a component. Now, whatever this color was is going to be replaced. And we only gain one if we have this color, if whatever this color was, like, isn't the same, or is the same as some other color adjacent to this edge. Because if we have some different color here, and say we have no red, then this was the only red one that was adjacent to this, which means having the red one gave us +1 to this node already. Or I'm going to actually use colors that make sense. Having this red one gave us this +1 already. Which means that changing it from red to blue doesn't actually do anything. Because now when we remove this red edge, we have -1. Right? So what this means is that the only way for this adding this edge to make a difference is if we already had a red edge adjacent to here, or whatever this color is. And the same goes for here. But that means that, like, it means we have a red edge adjacent to this node, and we have a red edge adjacent to this node, and this is a red edge, which means that this edge we're putting in is in the middle of the red component, which is, of course, not allowed. And if we extend this to beyond a single edge, it'll still work, because we have the same argument, that we have some like path of red edges from whatever node we have to the other node we're having. Or if we're doing like, yeah, we have some path of red edges, and we have some red edge here, and we have some red edge here. Which means that now, because we have a tree, and there's exactly one path between any two nodes, that these two red edges are going to be disconnected from each other, meaning that they're going to form two components, because the whole path between these two edges is being destroyed. Okay, so that's basically the idea of a proof that we can only affect at most one vertex. Because if we did more than one, it would be illegal. Still running on test 1. Okay. So my next claim is that we can affect any vertex we want. We can affect any vertex we want as long as it's already not at its maximum. Because like if it's not at its maximum, then there are two edges that are the same. So let's like replace one of the edges that are the same with the new color we get, and then because we disconnect this component, now we're gonna like replace the entire rest of this component with this color, like the entire rest of the red component, so that we don't have two red components anymore because the entirety of the red component becomes this color. So by the proof, this can affect at most one, and it does affect one, and it affects whichever one we want, because we can do this for any vertex as long as it's not already at its maximum. So what it means is whenever we get a new color, we can gain the value of any vertex we want that isn't already overloaded. So each time we go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, we gain the value of exactly one vertex. So now, basically, the strategy is simply greedy. We take the biggest value that isn't yet already at its capacity, that isn't surrounded by all distinct edges. And so we can do this by just sticking things in a priority queue and like removing it from the priority queue entirely if it's already at its maximum. That's the simple part. We just like at every step we start where we have the whole sum exactly once, and then at every step we can gain one vertex, for example this 6, as long as its degree is not the same as the number of distinct edges around it. And we can do that with a priority queue. Hopefully. If this ever finishes testing. See, that was fun to draw. Okay. Now we have E. I'm gonna leave that open. So these had like some large runtimes, and so did that. Okay, this is the next one. And well, this is the statement right here. Like they don't even need this subtext. This is just the statement. You have an array, compute this value. That is, compute the value of the sum from I equals 1 to n of the sum from, whoa, okay, that's terrible. Sum from I equals 1 to n of the sum from j equals 1 to n of the sum from k equals 1 to n of xi bitwise and xj times xj bitwise or xk. I'm not going to define bitwise operations. You can check this in the Wikipedia if you want to see it. So, like, just go to the statement and click these links. They'll describe what they are. So the first thing we normally think of doing with problems like this where we want the sum over a bunch of bit stuff is that we would normally go treat each bit independently. Like for example, because xi and xj is bitwise and xj or x, okay, wait. This is confusing. Because this operation is bitwise and this operation is bitwise, like sort of each bit is independent of the others. So we can sum the answer over all of the different bits. But the problem is the product is not bitwise. Like it's the product of two numbers. So that's not something we can do. But what we can do is try to mess with this equation a bit. Specifically, notice that this doesn't have a k term in it, and this doesn't have an I term in it. But j is included in both. So the first thing we might want to do is try and move j to the outside. And instead of rewriting this entire thing, I'm just going to copy this and do a bit of replacement. So we're going to swap the two sums, and we're going to move j to the outside instead. So now j is constant. j is constant, which means like this is just a constant. This is some value c. This is also a constant. This is some value c. And now this outer loop is O of n, which means we need to solve this whole thing in sub O of n, like some sort of faster thing, given that this is a constant and this is a constant. And that's nice, because if we had I on the outside, we would have a constant here, but now we still have something that depends on two variables. And this depends on that variable, meaning we can't separate it just as easily. How far did I go? Okay. Right. And the reason we can do this swapping is just because, like, this is just like we can swap these sums however we want, because, like, no matter what, we're going to iterate through all tuples of I, j, and k, where they're all, like, less than or equal to n, no matter what. Because these are just, like, names we give to the variables. We're always going to end up iterating through all tuples as long as we make sure we don't change the nature of the sums themselves, but we can switch their order around. So now the next question is, how do we solve this faster? So I'm going to actually get rid of this. And then now, notice that we have a sum that entirely depends on I, and a sum that entirely depends on k. And because j is constant, it means we can separate these. So we can separate this into, let me see if I can make this work. Move that there, move that there, and move this here. Yeah, perfect. Okay. Now we can do this. And the reason we can do this is because notice that these are like, this is basically just a value that depends on I, and this is a value that depends on k, because the rest of this is constant. So it's basically like summing up, if we create some new array A, where AI is equal to this, and we create some other array B, where BI is equal to this, then we're summing up essentially, this product is essentially sum from I equals 1 to n of the sum from B equals 1, no, k equals 1 to n of AI times BK. Let me use this color. Right, but like notice that AI is entirely independent of this. I don't know why I did this actually. This is enough to show this, but I'm just relating it to something that may already be known. Like AI is totally independent of this, and because like multiplication is distributive or whatever, because of like distributive stuff, we can move the AI outside. I equals 1 n of AI times sum from k equals 1 to n of bk. But like the idea is now, this is basically a constant relative to I, so we can, even though this is still within the sum, because this is also a constant, we can move this entire thing out to here. And that's how we're able to separate these. Like, am I going too in depth? This is just like math. You can just do this. Okay, so we have two independent problems. We want to compute this quickly, and we want to compute this quickly. So now, don't get too lost in the abstraction, or actually do get lost in the abstraction. We weren't able to go bitwise before because multiplication is not a bitwise operation, but now multiplication is totally independent of the bitwise stuff, meaning that now we can iterate bit by bit. So let's see, for example, for the 1 bit, what's the sum of xi bitwise and xj? So we have like two cases. If the 1 bit in xj is 0, then no matter what, this bit will never be included because like 0 and anything is anything else. But if it's 1, then nothing. But if it's 1, then we get the number of ones in total. Because it's essentially like, it's essentially xi and 1, but anything and 1 is itself, so now we're interested in the sum of xi, which is just the number of ones in total. So for each bit, like if the bit in the j value is 0, we get nothing, and otherwise we get the count of ones. But this is like something we can get in O of 1. So we can compute this sum in O of number of bits, because now we have some casework, and both of these things are O of 1, which is equal to O of log of like 2 to the 60th, which is just 60. And then the same goes here. Like we can do the same strategy for bitwise OR. So we consider the bit 1 in xj, and we consider every bit independently. Then if it's 0, then now it's the number of ones we have, because 0 or a 1 will still be a 1. So for every 1, we're going to gain something. For every 0, we don't gain anything, so we're interested in the count of ones. And if it's 1, then it's everything, because 1 or anything is itself. 1 or anything is 1, so we get n. And that's basically what we add. Then we add this value times the bit itself. So this would be times 1, or this would be 2 to the k, or whatever you want. This would also be times 2 to the k. And then for every j, we can compute these two quantities individually, multiply them, and sum that up over all j. And so this is what I'm doing, keeping counts of each bit, like so. And then for each value, first compute the and value. Like if this bit is set, you can do it with a bit of bitwise magic, like bit shifts and stuff. Yeah, if this bit is set, I'm not going to explain this. I'll leave you to try to work it out if you want. That's more fun to derive things. So if this bit is set, take the count. This is the and for the or, which I had left an enter here for some reason. If the bit's set, take n, otherwise take the count. And then just sum it up. Right, that leaves f and g. This had 20, f had 20 pretests. I'm like pretty confident in my idea. Oh, that's too far. Right. So again, G I did not get. As you can see right here, nothing happened. So that's not fun. Let me see how I was doing. Right, I was in 56. I was doing so well before G, man. That's just so annoying. And then I totally got screwed by G. It's kind of sad. But what can you do? Nothing. That's what you can do. Maybe I can be better at string problems, hopefully, soon. Okay, so this is like a scary mathy problem, but it's like not really that bad. Basically, the idea is, let's model it like this. We have n switches. So, for example, in the third sample, let's take that. We have 3 switches. A switch can either modify one, and we have like an array of a certain number of positions. So we have 5 like lights, for example. How am I going to do this? Say a square is on, or a square is off, and a circle is on, or something. This will make sense hopefully soon. Yeah. So we have a certain number of switches. Each switch can either toggle 1 light or 2 lights. So for example, this switch will toggle 1 and 2. This switch will toggle the 3rd light, and this switch will toggle the 4th light. And given that we can have any switch either on or off, how many different like configurations of lights can we have is the question. Yeah, how many different configurations of lights can we have? So the first step is like, which lights do we kind of have control over? Like, consider something like this. So because this switch affects only 3, like, using this switch, we can make 3 whatever we want. We can make this either on or off just by controlling this switch. And the same thing goes for 4. So we basically have control over these lights. And for any other configuration, we can make it so this light is either on or off. Which means like this adds, each of the lights that are already controlled add a factor of 2 to the answer. And what about the other ones? So for this is more like, well, this like affects both lights sort of at the same time. So like, these lights together can be on or off, but they can't be different. Which means that these 2 lights contribute a factor of 2 to the answer. So the answer for this is the product of all of these, which is 8. And so we sort of want to generalize this. And so the idea is that these lights are sort of connected with each other. And if we have some other switch that's like, for example, 1 in 5, then like all 3 of the lights are related to each other. Like 1, 2, and 5 are all sort of related because we can do whatever we want with them. So this whole group adds another factor of 2 because this one gives us more control. Alright, and so the general idea is like, this seems like a Linalg problem where you got like some sort of like some stuff that's not good, but it's like not that bad. And the reason is because we either have 1 or 2. So now the question is, like, these 3 are related, but how? And one thing we can do to represent relations between pairs of values is with graphs. So now let's draw a graph where each node is a light and the edges are the switches that connect them. So for example, like so. We have 1 and 2, and 1 is connected to 5, and these things are independent. Now, we have complete control over these 2. So these components are like, we can consider them solved, kind of. And the main other idea is that each of these edges also adds a factor of 2. And the reason for that is because, actually, how would I prove this? I'm not actually sure how to prove this. I'm sure it's like some sort of linear algebra stuff. Because the original representation is using vectors and doing like some fancy stuff, but I prefer to represent it as something that's like more intuitive. But I'm not sure if that works for proofs. So like we have 2's and some other things. I guess the idea is like, okay, so first of all, if we have a cycle, it's like irrelevant. Because notice that by activating this one and by activating this one, then ultimately this will be lit, and this will be lit, and this one will not be lit. Which is the same as just activating this one. So this edge is like entirely representable using these other 2 edges. Sorry, that cough. So this edge in the cycle is totally irrelevant, which means we can like drop it. We just get rid of it. And actually, the other part of the problem is to identify the irrelevant ones and get like a list of relevant switches. So get like the shortest possible list of relevant switches. So that's part of it. With any cycle, it's like completely irrelevant. And otherwise, so we can like assume that we're not working with cycles anymore, which means we have a tree of relations. then I guess the proof is like consider some edge that connects to a leaf. Now, nothing else affects this leaf, which means the state of this leaf is entirely dependent on whatever this edge is. So this can either be 0 or 1, and this can either be 0 or 1, and then whatever this is, considering the entire rest of the tree, we have like consider some function f that returns the number of ways this can be represented. Like f of tree is equal to ways or something. But we've shown that every leaf gives us a factor of 2, because essentially it's like we get 0. Like if we make this 0, we add f of tree, like tree minus this vertex, or without this vertex. And if we make this 1, then this is also going to be 1. But like every other configuration with the rest of the tree doesn't really care about this 1. It's just going to be like flipped in this bit. But because this is going to be a 1, all of these are going to be unique from all of the other ones, and we have the exact same number of ways to organize this tree, so we also have f of tree minus leaf, which is 2 times f of tree minus leaf. And so if we represent this as not like the tree itself, but just the number of nodes in the tree, then we get the recurrence f of n is equal to 2 times f of n minus 1, which just like proves that f of n, and of course f of 0 is just 1, because if we have an unaffected node, then we have nothing. So f of n is equal to 2 to the n. Actually, no, sorry, f of 1 is equal to 1, because if we have one node, then there's no edge connected to it. So f of n is equal to 2 to the n minus 1. So if we have a tree and none of the nodes are like solved, like none of the ones are connected to a switch with light that affects only one light, then like the number of ways we get is 2 to the n minus 1. And we want to take the spanning tree of this like sort of component, because any cycle is redundant. So we can find like a spanning tree, and that will give us the non-redundant ones. So the next question is, what if we do have a solved thing in a component? Well, then consider it being like this. We have this solved, or I mean solved like it's connected to something with switch 1. Or a better way to say it is like we can make it whatever we want without affecting the rest of the state. So if this one's solved, then no matter what the rest of these are, this can be whatever it wants. And that just means that like automatically this should imply that we get 2 to the n values now. If any node in the tree is solved, then we should get 2 to the n values, because we can get any possible state. But if that's not convincing enough, then I can go further. I can say that now because this is solved and we have control over this edge, I can make this whatever I want using just this solved node and this edge. And I can make this whatever I want using this solved node and this edge. So having a solved node in a component automatically solves all the other nodes. That's the basic idea. So with a solved one, then we get the full value of the component, which is 2 to the n, because we can make everything in a component equal to whatever we want. So if we have a solved component, we get 2 to the n, otherwise we get 2 to the n minus 1. And this aligns with this, which are components of size 1. And then the answer is the product of the number of ways over all components. Okay, now that gives us the answer. So automatically we have like solved half of it. But the other half is to restore a sequence of non-redundant switches. And if there are multiple, we want the lexicographically minimal one. I'm not going to define what that is because that's like very common, and this is F, so I trust you guys. But we want the lexicographically minimal set of switches, which basically asks what is happening with system test. So basically the idea is to find this sequence of switches, essentially every switch we include that's not redundant is going to add a factor of 2, because the reason that is because like every edge that isn't redundant will either connect 2 separate components or solve an entire component. And both of those things add a factor of 2. Because if we like f of n plus 1 is 2 times f of n, which is obvious. And so that means like for every switch we add into our like sort of system, we gain an extra factor of 2. So with that in mind, which switches are not redundant? Well, we want to include the first switch because that will give us the lexicographically minimal one. So we want to include the first switch if possible. And then we want to include the second switch if it's not redundant. Because if it's redundant, then there's no reason to ever include it. Like, that is, if it's not redundant with the system of only having the first one. Because if it's not redundant, then we'll want to include it. And it might make some other vertex later redundant, or it might make some other switch later redundant, but because every switch has the same value, adding some factor of 2, that's fine. So we can basically do it greedily. We can iterate from 1 to n, and we can try each vertex and see if it's redundant with the current system we already have. And if not, then we should take it, because A, that will give us the lexicographically minimal 1, and B, it's not going to hurt us in the future. Which means that it's going to be the best for constructing the lexicographically minimal 1. So now we simply need to check, given a system, is something redundant? And so this is where the graph representation comes in really handy. Basically, we have a bunch of components, and we have 2 operations. Solve a component, or like mark it as that we're done with it, and merge 2 components with an edge. Now this kind of sounds nice, doesn't it? Because this looks like DSU, isn't it? Like if you know DSU, then this is the second part is what we want it to do. And if you don't know DSU, you should learn it because it's kind of necessary, I think. So provided you do know DSU, this is what it needs. It will handle the merging part, but how do we handle the solving part? And so the better question to ask is, when do we actually want to connect to, when do we actually want to stick in a thing? When do we want to add a switch into our system? So we merge if A, they have to be in different components already, otherwise we would get a circle. So different components. DSU can easily check for that, so that's fine. But there's also no point in merging 2 solved components, because consider like adding this edge. But we can already make this whatever we want, and we can already make this whatever we want. And in general, we can already make everything in the 2 components whatever we want. So this edge gives us no more control of the components that we have. Which means there's no reason to ever merge any 2 solved components. But if one of the components is solved and one isn't, then that will add a solution to the other one, which is beneficial. And if neither of them are solved, then it will merge them, so that's still good. So we merge if A, they have to be in different components, and B, they have to not both be solved. So DSU can actually handle this too if we store an extra flag for our component for whether it's been solved or not. And then when we merge 2 components, if either one is solved, then the whole component should be solved. So that's basically it. And a separate wavy line, it should be this. A separate wavy line to say we should solve a component if the component's not already solved. Because if it's not already solved, then we'll gain a factor of 2 from it, and if it is already solved, then there's no point in solving it. Again, if it's been confusing, solving a component just means you can like make it whatever you want, because you have a switch of like that affects one vertex. You have a switch of size 1. And this is the only condition. We can solve it if it's not already solved. So basically the idea is go from 1 to n, check each switch, and check the switch's conditions. And if they're met, then we can add the switch into our system, and then use the DSU to handle this. Because solving a component is just setting the flag in the DSU to true. And checking these is just checking stuff within the DSU. So we greedily go from 1 to n and take everything we can and do stuff with DSU. So that's basically the idea. I have this DSU that does this, and I have it like activated instead of solved. Did some weird stuff there. So then just do the stuffs, and I have fast IO, right? That's like a thing. Okay. Like go from iterate in order, and then if there's like one switch, if the switch affects one thing, then just check if it hasn't already been solved. And otherwise you can check, like you can try merging it, and this merge will check that A, they're not in the same component, and B, they're not both solved. And that's basically it. Then just like print the switches you get. Okay, so is that gonna test my E now? Okay, so I got E, so we're just waiting on F now. And again, I was doing so well for almost the whole contest. Look at this. I would have gotten to 2,700 if not for this stupid problem G. Anyway, that's a bit disappointing. But whatever. What can you do? Nothing is what you can do. Wow. I gotta get like to Grandmaster or something. That's pretty good. Doing so well. Sad. Okay. And G. This is an idea. I'm actually not sure if it's. I'm not sure if I'm wrong or it's my implementation that's wrong. But I will go very briefly over what I thought would be true and ended up not being. So. Let's see. I don't see a point in reading the statement. So I'll assume you do know what the statement is, and basically the idea is to simulate the process until we get some huge string, like some string of length greater than 10 to the 6th. And then the idea is we have some x, and then we construct the string x plus ti plus x. So the idea is every occurrence of our query string in x is going to be doubled. And maybe we have some occurrences that cross ti. And so the idea is if we consider the occurrence that we're looking at, part of it's going to be ti, and the other part of it is going to be some prefix of x and some suffix of x. And it's going to be some character, and it's only going to match if the prefix matches, the suffix matches, and the character matches. And so the idea is like there aren't that many things to check. There are only O of n prefix and suffix pairs, because like it's just whichever character we decide is ti, and they're at most like the length of string, which is 10 to the 6 characters. So that's the idea of it. And then basically we can like figure out some math and figure out like for a given character, if this character is something like B, for example, we can figure out how much the character B being at like the ith iteration will contribute to the answer. And then we can sum that up over all characters B, and then if this character is actually B, then we can take the sum and we can consider that in our answer. And we can do a lot of pre-computation to do that sort of thing. And so we can also use some sort of hashing or something to figure out the number of occurrences in the original one. And Basically, the idea is to find the largest string in the process that's already greater than or equal to the string that we get in the query, the string w. And then we can do this sort of duplication math and also figure out the number of original occurrences using hashing or something, so that we can check every substring in O of 1. And then we guarantee that the string we're working with, like, what is it, si? The string we're working with, si, the length of si is at most, like, or like, the length of si isn't that much bigger than w. Because it's like the largest string in the process that we've done or it's the smallest string that's bigger than w. And the gap between two strings is like x becomes 2x plus 1, the length. And so like the string is going to be at most around O of 2 times the length of w, which means the number of strings we check is just O of the length of w. And the sum of the lengths is again 10 to the 6, so the complexity should work out there. My solutions did not have so great of a constant factor though. Like it was it was kind of close to the time limit, 1388 milliseconds. So I don't know how that would have gone if it had even passed the test. But from there, we just like we can figure out how much the original occurrence contributes. We can figure out how much like each sort of duplication occurrence contributes, and then we can do math to do everything. And in my code, I did a lot of mistakes, I'm pretty sure. A lot of things went wrong. But basically the idea is you do I did this with hashing. Like I did all of these checks with hashing. I'm pretty sure it's not the hash that crashed it, but who knows. And so you like explicitly generate the strings, make the hashes for all of them. I just computed powers of 2. Then you can sort of do the math for, again, if this character is something like b, how much will it contribute? And it's sort of like a prefix sum or a range sum from like the string that you decide on, like I, and then all the way up to the kth string. And then it would be like the prefix sums of the values of b. So you can do it like that, I guess. And then for each query, find the smallest string that's still bigger than it. This was a special thing I added in, but it didn't seem to make a difference. And then sort of for each query string, do this checking with this string x we get. And then find the characters that work for it, kind of. Because each occurrence will be like a separate time you add to the string. And so it's just like summing up this times the power of 2, but like if we want to sum up, for example, x times 2 to the k plus y times 2 to the like z, for example, and we want to do that quickly, then what can we do? Maybe that's why I was wrong. Actually, it's more like 2 to the, let's see, this isn't y, let's call this a. It's more like 2 to the k minus y and 2 to the k minus z. Maybe that was the mistake. Maybe I handled that wrong. K minus z. And then just like keep doing things. Well, the basic idea is you can use like negative powers or something. Like you can, maybe that's easier. You can just store like x times 2 to the negative y, and then a times 2 to the negative z. And then you can multiply all of that by 2 to the k at the end, and then you can get the formula you want. That's a way to do it. I did some other weird thing, like doing them all, like raising them to some huge power, like 10 to the 6th or something, and then bring them back down later. Not sure if that was the problem. And also, this is just finding the original occurrences. Yeah, I don't know. There was some mistake in my math or code or something. Ooh, running on test 50. Okay, so that basically does it. That is what I have for G. That's my idea. I'm not sure how wrong it is. Maybe I'll test it later and just like see if it's right, and if it is, I'll stick it in the description or something. And then maybe elaborate a bit more. That's the idea though. Okay, so we do pass all the system tests. I was in 50th at this point, and then just never came back from it. And then other people started solving G, and then everyone solved G, and I ended up in like 200th or something. But it is still IGM, and that I can be happy with. Even if it's a slight drop, it's still going to be above 2600. So that's cool. And apart from that, that's basically all I have. Those are the solutions. If there's a hello round, I'm not sure. I might do it. We'll see. This Div 2 I can't do because I think it's during school. And I'll do whatever rounds are possible. Whatever rounds come up. Probably not long challenges, but whatever comes out. Whatever like short contests come up. So anyway, that's all I got. Hope these were understandable enough, at least. And yeah, goodbye.